Now, the image you see behind me is Time magazine cover from January 1989, and it shows The Wrapped Planet by Christo. And at that time, the editor of Time magazine initiated an event that brought together scientists from all around the world, including 10 scientists from the Soviet Union. They all came to New York and they all agreed something must be done. And this was January 1989. So what went wrong? We're now here in 2019, and hopefully something will be done. And if people want to know why nothing happened after those meetings in early January 1989, I recommend you read this book, because it's very interesting how Naomi Klein describes what happened between 89 and the present. This Changes Everything, it's called. So I wanted to start by asking both my guests what they were doing in 1989. And it's really quite funny to discover what Robert was doing in January 1989.
So this came around last night when we were looking at this image, and I realised what the date of the image of the magazine. It said January 1989. I know exactly what was happening in 1989 because it was my third field season in Antarctica. It's a place called Dyer Plateau, and I'm going to show you a couple of images. These are two images of me in 1989. Now, the one on the left is me actually drilling an ice core. It's actually with a very old ice core rig. Everything I do now is much bigger, much more sophisticated than what you're seeing there. But this actually is the rig that we were drilling the ice that you're going to be looking at later on the ice floor, because the ice floor is ice that came from the 88-89 season, which is quite remarkable, that coincidence. And what you're looking at me doing there in the right-hand picture is actually running GPS survey. And that was one of the very first ever GPSs used in Antarctica. So the GPS that's in your mobile phone today, that thing on the right is its predecessor. It's a massive piece of kit. I had to lug it to the top of a mountain. It's got 2 car batteries in that red box, which we had to lug up to the top of the mountain as well. And that's the sort of thing that nowadays your mobile phone has got one of them that's 100 times more accurate than what I was using there. The other thing is I picked this one out of my archives. This is on the left, this is me, probably in 1989. And I'm now sitting in my tent, and we still live like this today. On the right-hand image, as you're looking at it, that's Shackleton in 1915. And just look at the similarities. So he's living in a tent. It's got a hooped front. My tent has got a hooped front. He's got his sleeping mat is draped over the top of the tent. Mine is also draped over the top of the tent. We still, to this day, lie on a sheepskin in the field. I'm sitting on food boxes, and Shackleton's also sitting on a food box. In the background is a sledge, just like Shackleton. And that was in 1989, but actually nothing's changed. And the interesting thing is, from a buildings point of view, from an architectural point of view, can you imagine buildings being designed in 1915 still being used today? What we designed as the way we live and work in the field in 1915 is still being used today. It seems kind of remarkable how little change we've actually made in that time.
In terms of your work, what was the most significant change you noticed in terms of climate change between 1989 and the present?
One of the things that people often ask me is, can you see change taking place in Antarctica? Normally, I'm in the middle of the field, in the middle of this continent. It's just a white desert. You cannot see any change from one year to the next. So this compilation of pictures. Now, in 1985 was the very first time I went to Antarctica, and I'm on a place here called the Gustav Ice Shelf, and it's an ice shelf that surrounds this little island here called James Ross Island. Now, the significance of that island is that when Shackleton was marooned in the Weddell Sea over here, he dragged his boats past James Ross Island, and James Ross Island's got a mountain on it called Mount Haddington, and I've taken this out of his diary. So this is actually out of Shackleton's diary, and it says, "A heavy blizzard obscured our view till March the 23rd. For the next 2 or 3 days we saw ourselves slowly drifting past the land, longing to reach it, yet prevented from doing so by the ice in between. And towards the end of March we saw Mount Haddington fade away into the distance." Now this is me here in 2008 standing on Mount Haddington looking out to where Shackleton would have been going past on the ice. There's water out there now, there's no ice left. And this is what happened in around about the mid-90s. All these ice shelves, now ice shelves are ice that just float off the continent. It's hundreds of meters thick, so it's not sea ice, it doesn't form every year. It float off the continent. but large areas of this sea ice have disappeared, and in particular, the ice shelf around James Ross Island disappeared. So back in 1985, in the right-hand corner, I was able to actually land and travel over that ice shelf. It's gone now. This is something I've seen change. It rarely happens right out in the centre of the continent that you can see change, but in the areas surrounding where they're close to the ocean, you can actually see that climate change taking place. And these are really rather remarkable images, I think, of huge changes taking place in the Antarctic continent.
1989, you started out...
I was into my sort of second year working, I was in my third job, in my second year working at Pilkington designing bolted glass systems. So this was the days when people were countersinking, drilling countersunk holes into glass, holding it up by confections of steel wire and rods and transparent walls and all that sort of thing. We were still using thick layers of toughened glass, hardly anything laminated, and still plenty of things which weren't double glazed in that time.
Right. And I'm going to ask the question a little bit differently to you. How, since then, do you feel has climate change affected the way you work? What is it in terms of the materials you use, the process, both?
Well, it's brought to our attention, particularly, especially to my attention, the impacts from the materials that we use. In making all of our, the majority of our construction materials, all the synthetic construction materials, the metals, ceramics, polymers, all of those involve carbon emissions, whether that's in energy use, making glass is, in St Helens they call it boiling sand, and that's essentially what you're doing. You take in silica sand, limestone, and soda ash, which is sodium carbonate, and they help it all help it melt and flow. And you heat it all up with a lot. They used to use fuel oil, and then nowadays they use natural gas to heat it. And as you heat it, it releases the carbon dioxide in the carbonate minerals. So that escapes up the chimney along with the combustion gases. Making cement, you take limestone and clay, do a similar process with it, calcine it, heat it until the CO2 comes out, and you've got... So both of those processes involve a big element of fuel to get everything hot enough, up to sort of 1,000 degrees kind of scale. And they also emit carbon dioxide just from the chemistry of what's going on to make the building material. And so what we're thinking about now is the embodied impact of those materials.
Would you say that's the most critical stage of the process of the construction industry to focus on in bringing down carbon emissions, for instance?
Well, we've been on a good trajectory of improving the operational performance of buildings, thermal efficiency of buildings, the insulation, the efficiency of the lighting and the services and so on. It was all improved to try and reduce the operational energy requirement. Meanwhile, our energy supply system, the electricity grid, has gradually decarbonised, and that sort of, you can see a trajectory. We'd love it to go faster, of course. But meanwhile, the building materials have now become a significant part in the overall life cycle carbon emissions of a building. It used to be that the operational emissions were substantially more than the embodied emissions. And as the grid has decarbonised and the efficiency of buildings has got better, now it's kind of the latest study, I think, from the C40 work was that we're at about 60% life cycle comes from the embodied emissions, and about 40% comes from the operational CO2 emissions. So it's becoming the significant thing to tackle.
And what would you say that Robert's work how can engineers learn, how can they use it, make use of the data that Robert collects?
We are taking note of those climate models. One of the things we're working on is creating tools so that we can project under various scenarios what the climate is likely to be in engineering performance parameter terms for different parts of the world. So if we're designing a building in a particular part of the world, what's the climate like now? What do we design for in terms of humidity and temperature and rainfall and all of that sort of thing? But what's it likely to be in 20 or 30 or 50 years' time? Because buildings have a long life cycle. You've got to design them anticipating not only statistical variations, but now also shifts in the climate, which are going to probably get, as they become a more high energy system, we're likely to get bigger fluctuations, and the things like rainfall and wind and so on are likely to increase in lots of locations.
Mm-hmm. Mm-hmm. There was one question I was going to ask you, Robert, how your work relates to water shortages in other areas of the world. I remember when I first met you at the British Antarctic Survey, you mentioned Africa. Can you just tell me a little bit more about that?
If you imagine Antarctica, it's a massive continent. It's the highest continent on Earth, it's the coldest, it's the windiest and so on. It also contains about 70% of the world's fresh water. Now, as climate changes and the climate warms, in fact what happens to the atmosphere is it takes on more moisture. So globally we'd expect to see more rainfall. So it may well be that one of the consequences of climate change or warming climate is in some areas of the world you actually might get to see more rainfall. So some areas of Africa might actually even benefit in that sense from a warming climate, because the greater humidity might lead to a greater amount of rainfall. It's, the models are very uncertain about this, but the more we learn and the more that climate models are developing, the more chances are we have of actually predicting that sort of thing. It's difficult to imagine doing what people often say, which why don't you just take some icebergs from Antarctica, tow them towards the equator and use that, melt it to provide water supplies. It's been considered, but it's quite an energy inefficient method of producing water.
Mm-hmm. You've brought something to show us today.
Yes, I know. Yeah, okay, I brought my lunch in a flask. You weren't expecting this, I know you weren't, but so I'll tell you what I brought along. I brought some ice from Antarctica. So this is the ice that I was collecting in 1989. How coincidental is that? So this is actually fairly shallow ice. At this point, air passes through it. But as it gets deeper, the air becomes locked off into discrete bubbles, and this is where I start to... I can hear this. Can you hear this?
Yeah.
Can you hear that? That's the air being released from the ice. So this ice is about 800 years old. So we're not long after the Norman conquest, I guess. I'm not sure if I know what king or queen was on the throne at that time, but you can hear it. Okay, so that's about 800 years old. So I've got a piece in here. Okay, this piece here. If you look at this, Jennifer, I don't know if the whole audience can see it. If you look at that, you see the air bubbles in there? They're quite large.
Yes.
They're much smaller in here.
Yes.
Okay, we're now deeper in the ice, and the bubbles have got much smaller because of the compression of the air on top of it, or of the ice on top of it. Okay, so you can hear it still. It's not quite as loud, but you can hear it. So this is 40,000 years old. So this has remained frozen in the ice sheet of Antarctica for 40,000 years. That was right in the middle of the last ice age until I drilled it. I actually drilled this piece this year. This was actually collected in January this year rather than back in 1989. But to me, this is where, the confluence between science, where I'm collecting this to try to understand the air and the atmosphere, the confluence with the art, because to me, I have an emotional attachment to this. It's just a lump of ice to you, but to me, there's an emotional attachment. I know how much effort it took me to get that, and how much pain my team went through to get this. But here it is, just melting away in front of your eyes. But I don't think you'll ever, probably none of you will ever see a 40,000-year-old piece of ice again.
Any questions?
Hi. Thank you so much. That was very interesting. My name is Anessa. I'm a lighting designer here at Arup. And I think we talked a lot about a bit of engineering and a bit of science. But tonight, I'm quite looking forward to experience the art of it all as well. I'm really curious to hear whether working with Wayne, you got something out of it as well, or were you merely, like the contributors to his art?
in my case, I'm getting something out of it. I mean, for me, he's able to express what... I'm not a very... art is quite a struggle for me sometimes. I'm a scientist. I tend to think very logically. I don't tend to think in an artistic way, but Wayne was able to take what I'm experiencing and somehow feed it back to me in a sort of amplified way that made me go, yeah, so I can emote about this, but partly because of this interaction we've had, where he goes, well, yeah, that's so exciting, you know, have you thought about it like this? And that interaction really changed the way I perceive the ice as well, I think. So yes, I got something out of it.
For me, it's been a fascinating experience, and working with an artist who's I detect was originally a musician, and I've had a lot of experience working with architects with very firm ideas about the form and structure and shape and all of that kind of stuff is pretty well formed by the time I talk to them, and I've loved the interaction with Wayne. And when the two of us went to first meet Robert at the British Antarctic Survey and see this ice, we spent days sort of bouncing around different ideas of how you might make something physical that represents what the ice means and Wayne's interpretation of it, and that has been a wonderful experience. And you know, I hope we've done it justice in some way.
So, having designed glass for this kind of projects, how are you going to take what you've learned on this forward to your design with glass in buildings in future?
I link between the ice and water and vapor, which we've talked a lot about in this in the development of this piece. It kind of resonates with thoughts about how we make glass a better insulator. You typically use glass in two panes of glass and a hermetically sealed space in between with very, very dry air in there, almost no moisture in there. And that stops it forming condensation, but it only lasts for so long, and eventually you get the seals leak and that humidity goes up and you get condensation. So it's this sort of contact with the ice and the cold and the water and the vapor has kind of encouraged me even more to look at other ways of making glass a good insulator. We can manage that space between the layers of glass, which provide the thermal insulation in new ways, better, with a longer lifetime than simply sealing them up and trying to make them hold their breath for 25 years.
Do you think there'll ever be a time when glass and steel won't be used so much in the built environment?
Well, I think there's a case for using renewable materials where you can, and then there's a good case for using timber in certain kinds of buildings for structure and for walls and floors. But steel has this marvelous combination of properties: the strength and stiffness and toughness. We can only use it at the high stresses that we do because it's really tough and it tolerates defects and it tolerates the way we use it and abuse it. And glass, it's non-combustible, it's transparent, it's pretty stiff, same stiffness as aluminium. It's a pretty efficient, if you want a material that you can see through, and we all want a connection with the outside world, if we can't actually be out there as much in it, as Robert gets to do, we want to at least be able to see it. So we need windows in buildings. So I think, and it is made from pretty abundant minerals. And if you could fuel the process of making it, if you could fuel the sand boiling with renewable energy, solar energy, and you could capture the carbon dioxide from the chemical reactions, then you could make it in a reasonably sustainable way, and it's a really useful material.
Thank you. I'm really looking forward to seeing the exhibition. It's a beautiful idea of kind of combining the art and the science and the engineering, and you've built it up really well, so can't wait to get upstairs. Just an observation about this division that we create between art and science. I've spent the last 9 years making films about Arup engineers. They're the most creative souls I've ever encountered. And I think the language we use often shapes the way we see the world. I think human beings are intrinsically creative souls, and I think everyone has that artistic bent in them. And the more we emphasize this division between I'm an engineer, I'm a scientist, I'm an artist, that kind of reinforces the division which really doesn't exist. And I think we much celebrate the creativity in everyone. And just an observation.
The graph that you showed that had all the dates back with the temperatures and the carbon, I think I've seen similar graphs when people have tried to say that climate change is a natural thing, and it has varied historically, obviously. But I'm assuming, is it the carbon that was increasing before the temperature, and if so, why has that happened?
Okay, this is actually quite a sophisticated scientific response. So the natural climate system is a natural greenhouse system. We rely on the fact there's carbon dioxide in the atmosphere to trap the sun's rays, or to trap the outgoing radiation from the Earth's the outgoing radiation from the Earth. So if you like, energy comes in from the sun and some of it's reflected back out to space. That has to be in balance to keep a balanced climate. Now we need a certain amount of energy retained in the Earth to keep it warm. If we weren't, our position in the solar system might mean that we're actually below zero. We'd be a frozen planet. So we need carbon dioxide. We've seen a certain level of it. What happens throughout time is the Earth changes in its orbit around the sun, and that changes the amount of energy we receive from the sun. That drives us in and out of the ice ages that I was showing in the picture. Now, if you calculate the change in the Earth's orbit, it equates to something around about 1.5 degrees Celsius change in the global temperature. What we observe is somewhere nearer 5 or 6. What's happening there is, if you imagine, carbon dioxide is either in the atmosphere, it's in the oceans, or it's in the biomass, the trees and on land. And that carbon is moving around all the time. Now, the carbon that gets absorbed by the ocean is drawn down to the bottom of the ocean. Marine organisms create shells out of that carbon dioxide. They die, they fall to the bottom of the ocean. As the climate starts to change, as we come out of an ice age, then what happens is that the ocean warms, and these carbonate skeletons at the bottom of the ocean are only just insoluble at ocean temperature. So as the temperature of the ocean starts to warm, then these are released back into the ocean as carbon dioxide. That enters the atmosphere, where it acts as a natural greenhouse gas, and we get this overshoot. So instead of 1.5 degrees, we get 5 or 6. So that's the natural system. The natural system, over at least the less 800,000, vary between 180 parts per million and 280. The problem is today we're at 410 or above. So for a long way outside the natural system. So the point is, it doesn't really matter in a way whether the carbon dioxide or the temperature changed first in the past. All that matters is the amount of carbon dioxide in the atmosphere. And it's really down to the physics of the carbon dioxide molecule. The carbon dioxide molecule vibrates at the same frequency of the radiation being emitted from the Earth. So I'm going to try not to bash Jennifer. So carbon dioxide, imagine my head is an oxygen atom, and these are 2 carbons. All that happens when the energy is released from the Earth is that these things start vibrating faster and faster and waving around like this. And that's the carbon dioxide getting excited by the energy being released from the Earth's surface. And that energy, if you do this, you warm up. Well, in a sense, the carbon dioxide does the same, and that's why the atmosphere warms. So it's not a case. So what we can do is we can build a climate model, which is where we try to predict what the future will be, and we say, okay, with increased carbon dioxide, we know from the physics of the molecule that it will put energy back into the atmosphere, warm the atmosphere. If we then take the model back in time and say, what happens if we started this 100,000 years ago or 500,000 years ago? Does our model work? Well, yes, it does. It works in the sense that with the levels of carbon dioxide in the past, we can predict the temperature in the past. So with the levels of carbon dioxide we're expecting to see over the next century, we can project into the future. So kind of what I'm saying is, yes, it's great that the climate system has got this natural cycle to it. What we've done is broken out of it by putting far more carbon dioxide into the atmosphere, which, because of the physics of the carbon dioxide molecule, has to convert outgoing energy into heat in the atmosphere.
Like a vocal cord or a reed, the sort of air moving past will wobble it from one extent to the other.
Yeah.
But it's fairly,
with
the extent of it is fairly steady, but it is always moving.
Yeah.
And what you're saying is, if we by putting a low more carbon dioxide into it, we are
Just
changing the tension in that
just
reed or
kicking it a bit
releasing it,
harder, yeah.
it's going to do something different.
You mentioned that Antarctica is losing ice mass. Is that loss happening across the whole continent, or is it just over a part of the continent? And do you think that the change in the mass balance will cause some sort of feedback, like runaway feedback or a tipping point?
In areas of Antarctica, we are seeing an increasing mass. But there are some areas, and one of them is an area called the West Antarctic Ice Sheet. The satellite altimeters, they fly over it routinely and they measure its altitude, and you can see that it's losing mass. You can't detect it in the field, you can't stand there and think, well, there's less here than there was last time I was here, but it is losing mass. Now that mass is then being converted to sea level. The sea level will rise because of that. And there is a sort of feedback loop there, because as sea level rises, it tends to lift floating ice shelves off their pinning points. So ice shelves often flow off the ocean, off the continent, and they're pinned by some rise in the bedrock, and they can't get any further. So they hold back all that ice behind them. And what tends to happen is, as sea level rises, then water can get underneath and it can start carving off the bottom of the ice. And then all of a sudden these things are floating and they can accelerate forward. And actually that's what happened in this area here. So these are ice shelves, and this is an ice shelf disappearing. So in a period of only a month, a whole ice shelf disappeared. So these things are floating on the ocean. So as they disappear, they're not adding mass at that point, because the Archimedes principle says, they haven't actually added mass because they're already floating. But as they disappeared, the glasses behind them then started to flow faster, and that takes ice off the continent that shouldn't be coming off, and then that adds to sea level. So there is a feedback effect. Wouldn't at the moment say a runaway one, but one of the things of interest in the West Antarctic ice sheet, which is not here, it's over there, is that we think it might have actually disappeared in the last interglacial, so the last warm period before the ice age. The temperature was about 1 or 2 degrees higher than today, so maybe where we might be in 100 years' time. But we think the whole of the West Antarctic ice sheet might have disintegrated and become sea level. And that would have added about 6 metres to sea level. And actually you can see that there is evidence in the world that the sea level was higher in the last interglacial. So the West Antarctic ice sheet is actually quite susceptible to this. It probably happened in the past, and a lot of the work I do at the moment is trying to understand whether that's actually correct, that probably, whether it did happen in the past. So yeah, it's a good question, and we hope it won't happen rapidly, but the potential is there for quite a lot of sea level rise should we lose. But that's not going to happen over our lifetime. The ice flows quite slowly, we kind of hope.
Yeah, I work with Wayne at the RCA, and I just wanted to say that it seems a really rich collaboration, the way between the Antarctic Survey, Arup, and the RCA, and with Wayne's work. It seems a new sort of collaboration. It's not like an artist going to industry and getting their giant sculpture made with, so it stands up. This seems a very creative collaboration, which seems very much to do with a new way of thinking because of the climate emergency. And I just wondered if, it feels very organic that everyone's relating to each other. It's not one person saying this, one person saying that.
The Phase 2 cultural programme at Arup has always been about the intersection of art, design and engineering, and that I guess becomes more pertinent when it's a topic like climate change, because people must be brought together. And I think, I'm still here at Arup, I'm still doing it, the Phase 2 programme, and I get a lot out of it because of this coming together of the different disciplines. But I think for this it's quite an emotive topic for people, and we've already had lots of resonance and feedback from people both within and outside the firm, because everyone's thinking about climate change. Yeah.
With climate change, I think people can sort of be paralysed by fear, because there's a lot of information out there and a lot of stuff happening that can be quite scary. So I suppose sort of finish on a positive note, either through our design or through the science, if you could have got an anecdote or a story of where we've done something differently to make a positive difference.
That's a good way to end.
I could think of two. I'll give you one of them. It's a British Antarctic Survey story. We discovered the ozone hole back in the mid-80s. At the time the ozone hole was discovered, industry understood, or science and industry understood, that it was the CFCs that were added to the atmosphere from things like aerosols and fridges and things. And at the time, the industry said, well, if you want fridges, if you want aerosols, you've got to have CFCs. There's nothing else. There's no other available chemical. And that, for quite a while, was the response from industry. There's no chance of it. And then one enterprising company found an alternative. And as soon as one had found an alternative, there was money to be made out of it because it had the only alternative available. And then all of a sudden, the whole of the chemical industry suddenly found there was a whole range of alternatives that they could propose. And now we don't use CFCs in fridges or aerosols anymore. So I think it's not a climate change story, but it's a story where industry actually eventually saw a profit to be made out of it, and I think maybe that may be the case with climate change as well. You can see industry, things like the alternative energy industry is increasing enormously. 20 years ago, it would have been hard to fund that sort of expansion in the industry. So for me, I have optimism.
I'm optimistic about what we can do in the design of our buildings and structures, and the recent study for which we did with C40 cities, looking at the embodied impacts of cities and the operational impacts. But in that, I mentioned the embodied carbon in buildings. That study showed that there was about an 18% reduction of that embodied carbon could be made simply by more efficient designs. So designs that just use enough material rather than plenty of material. And the reason I'm super optimistic about this is that when you look back 75 years or so, when materials were expensive and difficult to obtain, there was really intense work done on very highly material efficient designs. All the sort of super lightweight structures designs, all of that stuff was done in an era when people had been designing fighting aircraft and things with absolutely bare minimum of material availability and trying to get very high performance. And things were optimized to minimize the amount of material. We've been through decades and decades when material has got cheaper and cheaper and cheaper, and labor has got more expensive, so complexity has got more expensive. We're now seeing the real costs of these materials, and at the same time we've got the digital fabrication technologies allowing us to bring back some of that complexity. And we've got the design solutions which are much more complex if there's less material. We've got to marry that up quickly with these digital techniques to be able to make those more complex physical forms, which give us the performance we want with the bare minimum of material.
Good question.
Thank you.